Hello everyone, my name is Karis Sogarayamba and today we'll be looking at correlation, and this is to find what kind of relationship exists between two variables, two continuous variables. So for this tutorial we will look at the cars dataset, which is in base R, which is inbuilt in R. So we can load the dataset and we can say it's data and then cars. And then if we load it, and then we can look at the first 6 rows by using the head function. So we can see that at the below window we can see speed in one column and then distance, and they are both in continuous format. And this is a perfect example where we can use correlation to see the relationship between the two variables. And we want to see like how far the car traveled after the brakes were applied until it fully stopped. So how far the car traveled after brakes are applied. So the influence of speed on how far the car travels after the brakes are fully applied. There are different correlation methods. The first one is Pearson correlation, which is the most common one that is mostly used, which is linear correlation. We also have Spearman, which is rank-based correlation, and we also have Kendall, which is a concordance measure. But for this tutorial, we will only look at Pearson correlation. So our idea is to see what is the relationship or the influence of speed on distance. And R provides a correlation function called cor.test, which will give us the t-value, degrees of freedom, the significance of the predictor on the response. It will also give us the confidence intervals, and it will give us the correlation coefficient, how strong the two variables are correlated. So we can use the function cor.test, and then we placed our first variable, which is our predictor. So it is cars and $sign and then speed. Our second predictor, which is our second variable, which is our response, is the distance. Then after that we put the method. So this is where you can put Pearson, Spearman, Kendall. This is where you differentiate among the methods. But for our case now, we will use Pearson. And then if we run it, it gives us the t ratio or the t value, the degrees of freedom, which is 48, t value 9.464. The p value is very, very small, which is much lower than 0.001. And it also gives us the confidence interval 0.68 and 0.89, and the correlation coefficient of 0.8. It's also important to know that the correlation is positive. If there is a negative correlation, then there'll be a negative sign. So in our case, this is a strong positive correlation. Okay, we can also look at the same result but in linear model. So we can name our linear model as LHAM, and then linear model function, and then after that we put our response variable, which is distance, and our predictor will be speed, and then our data will be cars. So we run our model and then we take a summary of our model, which is LM. So The results are the same. The p-value is exactly same as our correlation test result. The t-value is just the same because they are both using the linear correlation, 9.464 and 9.464. The extra information that summary gives based on linear model is the estimate or the slope. So 3.9324, it basically uh, states that for each 1 mph, the stopping distance increases by 3.9324. So the influence of a unit of speed on distance taken until the car is fully stopped is 3 times. That's why it's 3.9324. Okay, we can also plot this. For plotting, we can use the library effects. And then before we go into plotting and just to visualize the results, it's also important to look at the intercept. So the intercept is minus 17.57 or 58. So uh, it basically states or say that at zero distance or at zero speed, the distance will be minus 17. So at zero speed, if the speed is zero, then the stopping distance of the brakes are applied will be minus 17.57. Of course, there is no distance as minus 17.5 feet, but this is what the model predicts. This is what the model predicts if the speed is zero. Okay, so we will use library effect. No, sorry, I have to put effects. Yes, library effects. And then after this we can plot. So it will be plot or effects, and then we can put our linear model, which is stored in the variable lm. So we have a basic visualization of the result. So speed is a good predictor of distance. So speed strongly influences distance. So it depends. Speed influences the distance that after you stop, the distance taken, it's more influenced by how much the car is speeding. Thank you for watching this short tutorial, and I will see you next time.